In this video, we will look at the fundamental theorem of algebra and complete factorization. So we've already seen that some nth degree polynomial can have at most n real zeros. Specifically, we might end up, after factoring a couple factors out, we might have something that's irreducible at that point, so we may have at most n real zeros. In the complex number system, an nth degree polynomial has exactly n zeros, counting multiplicity, and so can be factored into exactly n linear factors. This is kind of the punchline, if you will, of a lot of the work that we've been doing. We can take any arbitrarily complex polynomial, and if we try hard enough, we can factor it into n factors. So we'll look at the fundamental theorem of algebra, the complete factorization theorem, and then we will factor a polynomial completely. So the fundamental theorem of algebra says that every polynomial p of x equals a sub n, x to the n plus a sub n minus 1, x to the n minus 1, plus all the way up to a1x plus a sub 0 for n greater than or equal to 1 and a sub n not equal to 0, with complex coefficients has at least one complex 0. After looking at complex numbers and kind of refreshing on that, this should feel somewhat intuitive that if we have a polynomial, it could be as simple as just p of x equals x squared minus 4. It has complex coefficients, right, because the real numbers are a subset of the complex numbers. So this polynomial p has complex coefficients, and we know that it has at least one complex 0. So you should think of the definition here mostly in terms of, it needs to have at least one complex 0 because we're specifying that n must be greater than or equal to 1, and a sub n must not be 0. So we can say that every polynomial has at least one complex 0. Now, if we take this in addition to the factor theorem, which says that if c is a 0 of the polynomial p, then x minus c is a factor of the polynomial p, then we can say the complete factorization theorem, which says that if p of x is a polynomial of degree n greater than or equal to 1, then there exists complex numbers a, c1, c2, all the way up to cn, with a not equal to 0, such that p of x equals a times x minus c1 times x minus c2, all the way up to x minus cn. So now this just gives us the ability to use complex numbers to completely factor any given polynomial. And so to put this to use, let's just look at an example. Completely factor the polynomial x cubed minus 2x plus 4. So we'll find all the zeros and therefore completely factor the polynomial p. So let's start with the rational roots theorem. Since the constant term has factors plus or minus 1, plus or minus 2, plus or minus 4, and the leading coefficient is only plus or minus 1, by the rational roots theorem, we have possible zeros 1, plus or minus 2, and plus or minus 4. Now, if we use Descartes' rule of signs, this is kind of interesting because this will tie neatly into where we're going with this. We start with p of x equals x cubed minus 2x plus 4, and we have two sign changes, which says that we have 2 or 0 positive real zeros. Now I think when you remember complex numbers, some of these definitions kind of take on a slightly new meaning, right? When we look at p of negative x, we have negative x cubed plus 2x plus 4. And in this case, we just have one sign change. So for negative real zeros, we might have 1. So altogether, we have 2 or 0 positive real zeros, or 1 negative real 0. So now let's just use the remainder theorem, which, remember, we can take one of our possible real rational zeros, plug it into the polynomial p. If we get 0, then it follows that the number we plugged in is a 0 of p, and therefore can be factored out of the polynomial p. You could try a number of these. I happen to know what one of the rational real zeros are, so we'll just use that for now. So by the remainder theorem, we do p of -2, and that gives us -8 minus 2 times -2 plus 4, which equals 0. So -2 is a 0 of the polynomial p. So now we will factor that out. So we need a 1, a 0, since there's no x squared term, a -2, and a 4. Drop the 1 down. -2 times 1 is -2. 0 plus -2 is -2. -2 times -2 is 4. -2 plus 4 is 2. -2 times 2 is -4. And so we have 4 minus 4, which is 0. So this tells us that we can factor out the term x plus 2, and we're left with x squared minus 2x plus 2. Okay, so here's the fun bit. X squared minus 2x plus 2 is not obviously factorable. So now we should think, okay, quadratic formula, we can do that. So let me scroll down a bit. Now the quadratic formula, remember, we take negative b, so that'd be -2, plus or minus the square root of b squared minus 4 times a, which is 1, times c, which is 2, all over 2 times a. So this equals 2 plus or minus the square root. We have 4 minus 8, so that leaves us a -4 over 2. So now we can use complex numbers. And when we have the square root of -4, we get 2 plus or minus 2i over 2. So we have, finally, 1 plus or minus I. So these are the last two zeros. Now scrolling back up to see the Descartes' rule of signs, we see that we could have 2 or 0 positive real zeros and definitely 1 negative real zero. So this is the super cool part. This accurately predicts the case where there are complex zeros. So we had, for sure, we had 1 negative real zero and we had 0 positive real zeros. So now we can factor this in its entirety into p of x equals x plus 2 times x minus 1 plus I times x minus 1 minus I. And that is the completely factored form of the polynomial. So this equals x cubed minus 2x plus 4. Super cool. We can take any polynomial, arbitrarily large, arbitrarily complex, and factor it into exactly the number of factors as the degree of that polynomial. In the next video, we'll talk a little bit more about the zeros of any given polynomial. Just some additional tools to help us deal with specific situations and to verify some things that we're already intuiting at this point.